Hello, everyone. In the previous video, we introduced sequences, and now we're going to talk about convergence of sequences. Now, this video is not geared for real analysis students, so it's not going to be a technical definition of convergence. Instead, we're going to think about this more conceptually so that like calculus 1 or 2 students can understand it. So when we talk about convergence of sequences, what we're really asking is, does this sequence approach a number as n increases? So as we list more and more terms of this sequence, does this sequence get closer and closer to some number? If it does, then we say that that sequence converges. So a good way to learn about convergence of sequences is just to look at a couple sequences, one which converges and one which diverges. So here are two examples. Our first sequence is Sn equals n squared for n equals 1, 2, 3, and so on. And our second sequence is Sn equals 1 over n for n equals 1, 2, 3, and so on. Now, if we list off a bunch of terms of each of these sequences, then we will hopefully start to get the idea of, is each of these approaching a specific number? So here's our first sequence, Sn equals n squared. This sequence looks like 1, 4, 9. Next up, we've got 4 squared, so 16, then 5 squared, 25, then 6 squared, 36, 7 squared, 49, and so on. So does it look like this sequence is approaching a specific number? No, this is not approaching a specific number. So we would say that this sequence diverges. If we kept listing more and more numbers, this sequence would just continue to grow without bound. It would just march off to infinity. Now let's look at this second sequence. We've got 1 over n. Our first term is going to be 1. Our second term is a half, then a third, a fourth, a fifth, a sixth. We'll keep going. 1 over 99, 1 over 100, 1 over 101. Keep going. 1 over a billion, and so on. So, does this sequence look like it's approaching a number? The answer to that is yes. The sequence is approaching 0 because each of the terms is getting closer and closer to 0. So the terms are getting increasingly closer to 0. So we would say that this sequence converges to 0. So that's one way to think about convergence. We can list off a whole bunch of terms of the sequence and see if our sequence is getting closer and closer to a number. So here, this one was not getting closer and closer to a number, so it does not converge. If a sequence does not converge, then we say that it diverges. In our second example here, this sequence was getting increasingly closer to 0, and so this sequence converges, and it converges to 0. We can also say that the limit of this sequence is 0. So we would say that Sn converges to 0 because the limit as n goes to infinity of Sn is equal to 0. And if it helps, you can write in what is Sn. Sn is equal to 1 over n. So when we look at the limit as n goes to infinity of Sn, what we're really looking at is the limit as n goes to infinity of 1 over n. And we know that this is equal to 0 because as n gets increasingly larger, then 1 over n gets closer and closer to 0. So this we have seen two ways to think about convergence. We can list off a whole bunch of the terms. We can look at the limit And for people who are more visual, then I also think it is nice to look at this visually. So on the x-axis, let's have n. And then up on the y-axis, we'll have Sn. Let's mark off a bunch of tick marks. So we've got 2, 4, 6, 8, and so on. And then we'll put in 1, 1/2, 1/4, and so on. All right, so when we have n equals 1, then Sn is equal to 1. When we have n equals 2, Sn is equal to 1 over n, so Sn is 1/2. Then we've got a third, a quarter, a fifth, a sixth, and now we can see that as we move on and on and on, these pink dots are getting increasingly closer to 0. So we can see these dots literally converging in on 0. Okay, so I kind of like the visual way. It's always good to be able to write things as limits. And it's also good to see things more like conceptually like that. Okay, let's go back to our example, Sn equals n, I think squared we had earlier. And we said that this one diverges. And it diverges because it does not converge. So if we take the limit as n goes to infinity of Sn, what we're looking at is the limit as n goes to infinity of n squared. And we know that n is going to get larger and larger. So that means that n squared is going to get larger and larger as well. So this does not approach a number, or in other words, Sn, our sequence, grows without bound. Another way to say this is Sn does not have a limit. Now, if we wanted to make a nice pretty little plot like this, we can do that as well. So let's put in Sn, and then let's add in some marks on the y-axis. So maybe we've got 2, 4, 6, 8, 10, 12, 14. All right, so when n equals 1, then Sn equals 1 squared, or 1. When n equals 2, Sn equals n squared, which is 4. When n equals 3, we've got 3 squared, or 9. That's about here. When we've got when n is 4, then Sn is 16. So that's maybe about here. And so we can see that these pink dots are getting farther and farther apart as n increases. So here, these first 2 dots are just a little bit apart. The next 2 dots are a little further apart. The next dots are even further apart. If we kept going, we would need to draw our dots like all the way up here. They're just getting farther and farther apart. So these dots definitely aren't converging in on a number. So that is our visual way of seeing that Sn equals n squared diverges. All right, let's look at another example here. Our, I think, last example is Sn equals cosine pi n. So we're wondering, does Sn converge? So take a minute, pause this, and try to figure out if this sequence converges. All right, so one of the ways that we can see if it converges is we can look at the limit as n goes to infinity of Sn. When n goes to infinity, what is Sn? Well, Sn is cos pi n. So we're wondering, does cos pi n get closer and closer to some number? If it's not easy to see from this, we're going to see that no, Sn does not converge. And let's list off a few terms to see why. All right, when n equals 1, we've got cos pi times 1, and we know cos pi is -1. When n equals 2, then Sn is cos 2 pi, which is positive 1. When n equals 3, then we get our third term, which is cos 3 pi, which is negative 1. And so we can see that this sequence is just bouncing back and forth between positive 1 and negative 1. So this sequence is not getting closer and closer to any number because it's simply bouncing back and forth between positive 1 and negative 1. So this sequence diverges. So remember, anytime our sequence does not converge, we say that it diverges. So our sequence here diverges. It does not have a limit. All right, so if Sn doesn't have a limit, that also means Sn diverges. If Sn diverges, that tells us that Sn does not have a limit. All right, so now that we have an idea of what convergence means for a sequence, let's learn one rule for determining if a sequence converges. So there are lots of different ways for a sequence to converge, but this is one special rule, and we call math rules theorems. So here's one theorem. If a sequence is bounded and monotone, then that means that the sequence converges. So let's go through what each of these two words mean, because in order to apply this theorem, we have to check, is it bounded and is it monotone? Okay, so first of all, bounded. So here's our more mathy definition. A sequence is bounded if there are two numbers such that all the terms of the sequence are between those two numbers. That's all this is saying here. All the terms of the sequence have to be between two numbers. So for example, if we look at Sn equals 1 over n, and we write out a whole bunch of the terms here, we know that our first term is 1, then we have a half, then we have a third, a quarter, a fifth, and so on. So we can see that all of our terms are bounded between 0 and 1 because our biggest term is 1, and then our terms are getting closer and closer to 0. Or in other words, the limit of this sequence is 0. So all of our terms are stuck between, they're all bounded between 0 and 1. So we can write this like this. We can say that Sn is bounded between 0 and 1. Or in other words, 0 is less than or equal to Sn is less than or equal to 1 for all n equals 1, 2, 3, and so on. Okay, so Sn equals 1 over n. That is bounded. Let's look at another example. Cosine pi n, that one was also bounded. So remember, this is the one where we had -1, +1, -1, +1, -1, +1, and so on. So all of our terms are bounded between -1 and 1. So here we have two examples where our sequences are bounded. If we want to think about an example where our terms are not bounded, we can think about Sn equals n. For this one, we have a lower bound. Our lower bound here is 1, but this doesn't have an upper bound. And we need to have both an upper bound and a lower bound in order to say that a sequence is bounded. So Sn equals n is not bounded. All right, so here we have two examples with sequences that are bounded. And then this last example here, the sequence is not bounded because we do not have an upper bound. Okay, so now that we understand what bounded means, let's look at our definition for monotone. So a sequence is monotone if it's always increasing or always decreasing. So we need to have either increasing or decreasing. let's take out the word strictly just to make it a little simpler. Okay, so if our terms are getting bigger and bigger and bigger and bigger, then we'd say that our sequence is increasing. So makes enough sense. Each term is getting bigger than the last, so the sequence is increasing. If each term is getting smaller than the last, then our sequence is decreasing. So that's all this is saying here. Here in this square, we're saying that the terms are decreasing, they're getting smaller. And here we're saying that the terms are increasing or getting bigger. Okay, so if we have a sequence that's decreasing, then it's monotone. If a sequence is increasing, it's also monotone. If a sequence increases for a while, then decreases, then increases, and then decreases, that's not monotone. We need to have only increasing or only decreasing. Okay, so let's look at a few examples of monotone sequences. Here we have Sn is equal to log n. And the terms of this sequence are increasing. And if we plot it out, we could see why. So if we have n equals 1, then S1 is log 1 or 0. When we plug in 2, our second term is log of 2. That is bigger. Then we have log of 3, which is even bigger, log of 4, which is even bigger. All these terms are getting bigger than the last. So the terms of this sequence are increasing, and they never decrease again. So since they're only increasing, then our sequence is monotone. Our theorem that we described earlier, we said that we need to have monotone and bounded. And this is an example of a sequence that is monotone because it's just increasing, but since this is not bounded, we cannot apply our theorem. Okay, let's look at a couple more examples here. So here we have Sn is equal to 4 to the n. And this sequence, is it bounded? No, it's got no upper bound. Yes, it has a lower bound of 4, but there's no upper bound. There's no upper limit to this sequence. So this sequence is not bounded, but it is monotone because it's only increasing. Okay, next example, we've got Sn equals 1/4 to the n. And this one is bounded. It's bounded between 1/4 and 0. So yes, it is bounded, and yes, it's monotone because the terms are getting smaller and smaller. In other words, this sequence is decreasing, so it is monotone. So our theorem said that if it's both bounded and monotone, then the sequence converges. So we now know that our sequence right here converges. All right, so in this video, we learned about the definition of bounded and monotone. And when we have a sequence that is both bounded and monotone, then we know that it converges. There are other ways that a sequence can converge, but here is one way to know that a sequence converges.